All right, Chem 212 students, welcome back for the second video on substitution and elimination. When we finished last time, we were talking about the stereoselectivity of E2 reaction. In this case, we can see that the trans uh, the trans configuration ends up as the major product in the elimination versus the cis configuration, assuming that both configurations are possible. In some situations, due to the way that the E2 reaction occurs, depending on the molecule, there may not be two products that can. There may only be one stereoisomer form. This is what's referred to as stereospecificity. This is because while the pi bond is being formed, remember what a pi bond is. A pi bond is formed from the sideways overlap of unhybridized p orbitals. On our substrate, when we start, there are no unhybridized p orbitals. Both of these carbons are sp3 hybridized with 4 bonded atoms and no lone pairs. And so, for certain molecules, when it comes to performing the elimination, when the proton is removed, there's only one possible proton that can be removed. And when this is the case, the molecule must be in a specific conformation for the reaction to be able to complete and ultimately produce two sp2 carbons that have unhybridized p orbitals in the sideways overlap position. And for this to happen, the hydrogen here, that's the beta hydrogen that's being removed, and the halogen or other leaving group must be positioned in a so-called anti-periplanar arrangement. And this is what's demonstrated here in this diagram. We have hydrogen here, which is in the same plane as the bromine, but they're in opposite directions. And this is what is the conformation that the molecule must get into for the reaction to even occur. So you might imagine here that it would be possible to produce both E and Z products. We can't say cis and trans here because there's 4 different groups, but you might think that it's possible to form both E and Z products. But the answer here is that in this case, you can only get one product. So here, this is the product where the phenyl and the hydrogen are on the same side of the double bond, and the methyl and the terbutyl are on the same side of the double bond, as opposed to the other isomer, which cannot be formed. This is referred to as stereospecificity. And let's talk about the way in which this occurs. The transition state in the transition state, the carbon hydrogen bond will be beginning to break. The carbon bromine bond will be beginning to break as well, and the carbon carbon double bond will be beginning to form. And this must all occur at the same time in an E2 mechanism. So we say that the beta hydrogen, the leaving group, must be coplanar, meaning they're in the same plane. So there are two rotamers where the beta hydrogen and the leaving group are coplanar. They're either in the position where here the hydrogen is directly opposite to the bromine, or if we rotate everything around by 180 degrees, put this hydrogen in the same plane, so we're rotating this straight up, then the methyl will be out here on the wedge, phenyl will be on the dash. And this is another situation where they're coplanar. However, one thing to note here is that to achieve this configuration that we're seeing on the right, which is referred to as syncoplanar, where the beta hydrogen and leaving group, the bromide, are on the same plane, they're going to be in this eclipsed conformation for that to occur. However, if they're anti-coplanar like this, everything can be in the staggered conformation. We learned in chapter 4 there's a significant energy cost to getting everything in eclipse conformation like this. And so at any given time, very few of the molecules will be in this configuration. And so we can expect the vast majority of them to be in the anti type of configuration. So this is the lower conformer or rotamer energy is the one with the anticoplanar H and Br, and the syncoplanar is the higher energy rotamer. So the result is that we're not going to see a lot of reactions happening from the syn coplanar situation, because very few of the molecules are in that in the form of that rotamer. Most of them at any given time are going to lower energy. And so, uh, practically speaking, the product is going to be the only product that's going to be made is the one that is in the anti-coplanar type of arrangement. And notice something that occurs here. So as this reaction is occurring, remember there's a carbon-carbon double bond being formed between this carbon and the back carbon. So it's going to become trigonal planar, meaning that these phenol and these hydrogen are going to become closer and closer to the same plane over the course of the reaction. And in this case, the methyl and the terbutyl are going to become closer and closer to the same plane. And then so this is looking at it from a view from the, like from here, or eyeball here. In this case, is kind of looking at this product from this perspective right here, methyl and the phenol being in the front, and the terbutyl and the hydrogen being in the back. Eventually, they're in the same plane. So the methyl and the phenol are on one carbon in the same plane as the terbutyl and hydrogen. And so the way I think of this is when you do need to draw the Newman projections for these usually to figure it out. And then whatever you have on either side, everything just kind of flattens out. And those end up on the same side of the double bonds. In this case here, you can see the methyl and the terbutyl are on one side of the double bond here, and the phenol and the hydrogen. Now, that said, we use the term coplanar, meaning that the beta hydrogen and the leaving group are in exactly the same plane. In fact, they don't need to be in perfectly the same plane. They just need to be close to it. So the word for being almost planar is periplanar, almost in the same plane. And we want not necessarily anti-coplanar, but anti-periplanar, very close to the same, being in the same plane. And although an E isomer or a trans isomer would be usually more thermodynamically stable, because of the issue here where the groups, the hydrogen, the beta hydrogen, and the leaving group have to be anti-periplanar, often we can only get one stereoisomer product. And so that may not be the more stable product. The less stable the product is, slower the reactions go. However, there will only be one product in these situations where you only have one beta hydrogen that you move. You will not get the other stereoisomer. So let's think about what will be the products here when this occurs. Remember that we said that whatever's on this whole thing is going to flatten out, right? So when we have a base here, base is going to come, it's going to take the proton. Proton's going to leave the electrons behind, which will become the electrons for the double bond, and the leaving group will leave it. So when we get the product here, the red ones are going to be on the same side. So we'll have here R1, R1. So these being the front, let's call the bottom here. So this is like the front. This is the front where the wedges are sticking out. These are going to be on the same side. It's just going to flatten out to where these R groups are in the plane of the page. And then the R2s will be here. That's the only possible you can have. Whereas here, if we have this other arrangement, it's the same thing. We'll have a base. That base will do a proton transfer, and that one will leave its electron here and then leave. In this case, the R1 and the R2 are on the wedges. So if we call the front the bottom here, then R1 here on this left carbon will be on the front, R1, and then R2 will be on the second carbon, the one on the right, on front. Then in the back here, we'll have R2 on this one. So notice that there's only one possible configuration, right, that can occur. It depends on where these groups are relative to one another in their three-dimensional space here. But you always just flatten it out, and I like to do the wedges on the bottom and the dashes on the top. Blocking it. Okay. So in this case here, we can see that we can get both stereoisomers, right? Because we have two hydrogens that can be removed. So when there's only one hydrogen that we have stereospecificity. So because there are two hydrogens that can be removed, we now have not stereospecificity but stereoselectivity. We can have either of these hydrogens removed. If here we have this bottom hydrogen, so if this is the base here, and it's taking this hydrogen, then in this case the wedges here will be the R1. Let's see, the R1 and the R2. In this case, they've been put at the top. So here the R1 and the R2 are top. So this is the front, and we can see that the R1 and the R2 same side, and then this hydrogen here and this R3, which are both on the dashes, back, these end right here. Now, if we rotate this, however, and put this hydrogen in the plane of the page, that's going to put the R1 on the dash and this hydrogen on the wedge. So we rotated this a little bit. This hydrogen would be on the wedge, and so would the R2, and so we'd end up with them on the front here, the hydrogen and the R2 on the wedge. That's if we pull this out just a little bit. So if we just take this hydrogen and we pull on it, we pull it out this way, that's going to put this hydrogen on the dash here and pull this hydrogen, in the wedge. So this is going to be a wedge, and this one's going to go back, dash now. So we can see that the R1 dash and the R3 is the dash, so that's the back. Those are on the same side. Whereas here, the hydrogen is in the front. It's now a wedge because we pulled it forward, and also on the wedge is the R2. So those front there. In this case, the reaction will be stereoselective, but not stereospecific, right? Because we have two beta hydrogens. You have to watch out for stereospecificity when you only have one beta hydrogen. You have to watch out for it. There will be a problem like that. Guarantee it. I do want you to know about stereospecificity versus stereoselectivity. It will be stereospecific when there's only one hydrogen. It will be stereoselective when there's more than one. So stereospecificity only occurs also when the alpha and the beta carbons are both stereo, right? Otherwise, it won't matter. So it's very important to understand the difference between, right? When we have a stereoselectivity, we'll have a major and a minor product. When we have stereospecificity, there's only one possible product. That's the idea. Now, when it comes to a cyclohexane, so remember the chairs and the boats, right? And we have to consider that what would happen there. In the case of a cyclohexane, you can only have the anti-periplanar when the cyclohexane ring has the leaving group and the hydrogen in the axial position. Notice that there's not going to be a hydrogen that's anti-periplanar when the chlorine is in the equatorial position, because those hydrogens here, there's actually going to be a carbon that's not a hydrogen, right? Whereas here, the hydrogen here is axial. So you cannot have an E2 elimination when the leaving group is in the equatorial position. It must be in the axial position, which can place it anti-periplanar to a hydrogen. So if let's say we had two examples here and ask which one would undergo an E2 reaction, wouldn't, right? Remember that axial goes up, down, right? Up, down, up, down. So since the chlorine has to be axial, let's say we call this one, this is the axial position. Axial, we're going to put this chlorine axial. And we're going to say that this is a wedge, so this is up. And so on the neighboring hydrogens, the axial position will be down. So this will be the axial hydrogen. This one will be equatorial. The axial. Equatorial. And so in this one would undergo E2. It will do E2 because the hydrogen can be axial and down, while the chlorine on the neighboring carbon is axial and up. However, here, the methyl, so axial is up, so on the neighboring carbons, axial will be down. So the methyls will be at the axial position. And the hydrogens will be equatorial in both of these. So we'll get no E2 reaction from this molecule. So that's something to keep in mind. You do have to remember your axial goes up, down, around the ring, right? We didn't necessarily have to draw a full chair conformation, but you have to be aware that if whatever the position here is for your leaving group, make sure it's axial. You call that position axial. Then look at where the hydrogens are. The hydrogens also have to be axial. Remember, axial goes up, down, all the way. Okay, so in this case here, this E2 reaction is very slow. It basically doesn't really occur very quickly. Why is that? Let's see. Well, it's because here we got this big group here that makes it so we can't do an elimination here. The reason is because remember that the hydrogen has to be antiperiplanar. So this chlorine here, since this is down, we're going to call this down and axial, then axial is up here. So this wedge is axial, and the hydrogen is equatorial. So they can't be antiperiplanar there. We have two hydrogens here. So the one that's here, this one is also going to be axial. So then we can get a double bond here. However, this reaction, so this reaction is slow because notice that the product that we get is not very thermodynamically stable, right? It's only di-substituted. And so we're not going to get a hugely fast reaction. It's not an extremely stable product. However, when it comes to this situation here, now the chlorine is up axial. And so this hydrogen here is down and also axial. And so now they can be antiperiplanar. So now you don't have the stereospecificity anymore. You only have the stereoselectivity. And here, this one will be much more, this one here on the right will be stay more stable due to this hyperconjugation of this large group here attached. It's tri-substituted again. Notice this is only di-substituted, right? So there's a hydrogen here and there's a hydrogen here. So it's only got two carbons attached. Here, it's tri-substituted. One carbon here, one carbon here, one carbon here, only one hydrogen. And so you get a more stable product here going in this direction. So this one will occur much more quickly. And this will be the major product here. Minor one. When we draw the products of the E2 reaction. So we have to be very careful. We have to double check here. Is there going to be stereospecificity? This is when you have both carbons are chiral and there's only one hydrogen on the beta carbon. Then you'll have stereospecificity. E2 reactions will be stereoselective to produce the trans isomer rather than cis, right, due to greater stability. And then you have to think of regioselectivity, right? So here we had an example of regioselectivity. Here, this being a non-sterically hindered base, having the Zaitsev more substituted product here was more favorable. We have if we had a sterically hindered base, the Hoffman product, the major, less substitute. Okay, and finally, now we've covered SN2 and E2. These are bimolecular reactions. Substitution and elimination can also occur in a unimolecular fashion. These are referred to as SN1, meaning nucleophilic substitution, uh, unimolecular, and elimination, E1, unimolecular. In these unimolecular reactions, what we're going to see is that the leaving group leaves first. And we can ultimately have, again, like with E2 and SN2, for any substitution or elimination reaction, we can have either product. We can replace the leaving group with the base/nucleophile here. Here it's ethoxide, so the bromine is replaced with the ethoxide. Or we can have a elimination in which a double bond is. So when we look at the substrate here, the substrate is tertiary. So SN2 is going to be extremely slow. It's just not going to happen. The ethanol here is not a strong base. So we don't see elimination as likely either. So there's going to have to be another reaction mechanism that would have to occur for these substitution and elimination products to be made. And these are going to go through the first order reaction kinetics, in which the rate is dependent only upon the concentration of the substrate. And this is because this is going to involve a two-step mechanism, and the slow step will be the one in which the leaving group leaves, which will be the first one. And so only the substrate will be involved in that step. The nucleophile or the base will not, and so it will not be included in the rate. So again, these are easy. SN1 and E2 are two-step mechanisms. So remember, the 1 and the 2 don't mean how many steps. In fact, quite the opposite. They mean how many molecules are involved in the slow step. And here, the slow step is the first one in these mechanisms, and this is the one in which the leaving group leaves. So you can understand why this might be slow, right? First, we have to break a bond. That costs energy. So that's not usually thermodynamically favorable. Also, we end up with an intermediate that is somewhat unstable. So we end up with a carbocation intermediate because the leaving group leaves and it leaves the carbon with 3 bonds pairs. So that leaves a carbocation intermediate. So here's the way a SN1 mechanism goes. So again, first the leaving group leaves. So we can see here the leaving group is leaving. We got these bond breaking and these electrons left. You'll notice here a type of notation that says minus Br minus. This is just saying the leaving group leaves and we're not going to think about it anymore. Minus means taking it out. It went somewhere else. It's not doing it. Then ethanol, which is a nucleophile, it's not a base, but it is a nucleophile. It attacks. It has a pair of electrons that can be donated to this carbon to make a bond. And so the nucleophile attacks, and we get a bond between oxygen and hydrogen. Now the oxygen here has 3 bonds and 1 lone pair, so it has a positive formal charge. So we end up with another unstable intermediate here. So in this case, there's going to be one more step, and that's going to be the removal of an additional proton from the leaving group, because the oxygen here has this positive charge. We still have ethanol in here. Ethanol can function as a base. It's not a great base, but we have here a proton transfer where this lone pair makes a bond with the hydrogen, and then that leaves these 2 electrons of this bond behind on the oxygen, now giving it again to get the substitution. So the actual mechanism is actually 3 steps. The last step is just a proton transfer. And there's a name for this type of reaction, which often occurs in SN1 reactions. Is we call this solvolysis, where the solvent is the nucleophile. In this case, the ethanol is the solvent. It's also the nucleophile. And so that makes a situation where there's lots and lots of nucleophile, which does speed up the parts of proton. So here's an energy diagram that represents this. And as I said, I'm going to have you draw an energy diagram like these on the exam. Remember that the horizontal axis is called the reaction coordinate or reaction progress. The vertical axis is relative energy. And there are 3 steps here: the loss of the leaving group, the nucleophilic attack, and the final proton transfer. So since there are 3 steps, we have to have 3 bumps. And our intermediates are this carbocation here and this reactive intermediate here. And so those are what the troughs are going to represent. And so here we have the first step, which is a loss of the leaving group. Notice the activation energy high here. That's why it's the slowest step. And then we produce a semi-stable intermediate, this carbocation, that undergoes a nucleophilic attack where the nucleophile attacks, and we get a somewhat stable product here. However, not quite as stable as it could be. We could get rid of this positive formal charge with a proton transfer. Third step, the third bump. So remember, the number of bumps is the number of steps, and in between each bump, there's going to be a trough. Those represent the reactive intermediates, and the peaks represent the transition. So the first step here, look at the huge activation energy. First step in the SN1 is the step, and it only depends on the concentration substrate, and so that's why it's SN1 unimolecular. Only depends on so the rate is the rate constant times the concentration of only the substrate. Again, the concentration of the nucleophile does not matter here. That's why it's unimolecular. So nucleophilic substitution. That's how you one. So notice that in this reaction, a carbocation intermediate is formed. And remember, we were talking about the relative stabilities of carbocation intermediates, and we said those that are tertiary are the most stable. And so you can see this is in fact a tertiary carbocation. This carbon is attached to 3 other carbons. Well, this is fortuitous. If we want to do a substitution on a tertiary carbon, remember that SN2 is not good for a tertiary carbon because it's going to be blocked on the backside from the backside attack. And so an SN1 reaction instead. So remember also that when the nucleophile is a neutral species, such as an alcohol, there will be a last step where that is protonated. That was shown right here, just going back again. If you have a neutral nucleophile attacking, there's going to be an additional proton then afterwards. So there will be a third step in those. So that's SN1. Let's talk about E1 now. So if we have a strong base that's involved, we could have an E1 or a base of some kind. So in this case, the ethanol can act as a base as well. So the alternate reaction pathway here is that after the leaving group leaves, notice the first step is exactly the same as before. We get this tertiary carbocation intermediate. At that point, the ethanol could attack as a nucleophile. It could also remove a proton from the beta carbons. This is the alpha carbon, this is the beta carbon. And so we have a proton transfer. This lone pair here makes a bond to the hydrogen. These electrons are left behind. Nation product. So here the ethanol is acting like a base. It's removing a proton. But also the E1 mechanism is unimolecular because it's the first step, which is rate determining. That's the loss of the leaving group. You can see that right here. It's the same first step. So the rate of in the case of E1 and SN1, the rate is going to be the same in most cases because the rate is going to depend on the first step. Right? So in the first step for the SN1 and the E1, as you saw, is the loss of the leaving group. It's the same. So here's an energy diagram comparing an SN1 reaction, the SN1 reaction that we just looked at versus the E1. So they both have the same step, which has this higher activation energy. It produces the carbocation intermediate. After that, we can have either the elimination or the substitution. In this case, the substitution produces the lower energy product with a lower activation energy for the step, and so it would be the preferred product. So because there's a carbocation intermediate here, we have another situation that can occur. Remember, one of our steps, we had 4 different types of reaction steps. It was loss of leaving group, nucleophilic attack, and proton transfer. And we've talked about all of those so far. The fourth one that we haven't talked about is, in this chapter anyway, is the carbocation rearrangement. So rearrangements can occur in SN1 and E1 reactions because there is a carbocation intermediate that does not exist in the SN2 and E2 reactions. So for example, if we react this alkyl halide with water, water is going to be our nucleophile here, and so in this case here, we can either have the water replace the bromine here, but notice there's a carbocation intermediate in this step, right? When the leaving group leaves, like the bromine, we end up with a carbocation intermediate right here. And now we have the situation where there's a hydrogen, and this can undergo a carbocation arrangement. This is a secondary carbocation. If this hydrogen is here, then we will have a tertiary carbocation right here, because now this carbon will have 3 bonds and lone pairs, so it will be tertiary carbocation. And then at that point, the nucleophile can attack right at the positive part right there, and that means the OH here would attach to this tertiary carbon instead. And so we'd get actually more of this product because the tertiary carbocation is stable. In addition, similarly, we could have, instead of a hydrogen shift, we could have a methyl shift, which would produce a similar situation, except we'd have a methyl over here, hydrogen. So when a primary substrate is reacted here under the solvolysis condition, we're going to see extremely little of the product in which the bromine is directly replaced by itself, because again, if we have the loss of the leaving group here, what we have here is we have a primary carbocation, extremely unstable. So what would happen quite readily is that we'll have a methyl shift, and at that point we'll end up with this tertiary carbocation, methyl now. But this carbocation will be tertiary, and now that's much more stable, and so the nucleophile will attack that tertiary. So we'll end up with the one where the OH is attached here on this carbon rather than. So the thing is that primary carbocations are very unstable to form. So realistically, what's probably going on is the methyl shift is occurring simultaneously as the leaving. You don't have to draw it that way. So here I drew it as 2 steps: the leaving group leaving, and then the methyl shift. Here in this diagram here, bottom, it's showing the methyl shift occurring simultaneously with bromine, with the loss of the bromine. Realistically, that's probably what's actually because the primary carbocation would be extremely unstable just to form it. So this kind of would help it along with the same time. And of course, after the water attacks again, this is another example where we have a neutral nucleophile. And so we end up with this oxygen with 3 bonds and no pairs. So there's one more step at the end, protonated. So one thing that we haven't talked about yet in terms of deciding too how a reaction will occur, we've talked about the substrate, whether it's primary, tertiary, secondary. We've talked about the nucleophile or the base, right? We've talked about the leaving group, the quality of leaving group. One thing we haven't talked about is the effect that the solvent may have. So experimental data indicates that SN1 and E1 reactions are faster in a protic solvent. So a solvent in which you have an oxygen attached to a hydrogen, right? Or a nitrogen hydrogen, but generally oxygen attached to a hydrogen. Protic. So we can see here, if our leaving group is iodide, bromide, chloride, fluoride, in a in a protic solvent, methanol. So methanol has oxygen attached to hydrogen. That's why we can say protic. Here, this is the rate of the SN2 reaction. The SN2 reaction will occur much more quickly in a polar aprotic solvent. So that means that it's less competitive with the SN1 reaction when there's a protic solvent. So we can see the SN2 reaction occurs much more slowly in the protic solvent. And we're going to talk about why that is. But what we would want to do is, if we want the reaction to occur under the SN1 and E1 mechanism as opposed to SN2, we would choose a polar protic solvent because this will reduce the speed of the SN2 reaction. And thus the SN1 and E1 reactions will become more competitive. And why is this? Well, what we're concluding here is for SN2 reactions, you want to use a polar aprotic solvent. And what's shown here is DMF, dimethylformamide. We'll look at the structure of that later. It doesn't have an OH. For SN1 reactions, we want a polar protic solvent. And so why is that? Well, it's because if we have a polar aprotic solvent in an SN2 reaction, the reactants start at a higher energy. So the activation energy is lower, and you get a much more exothermic reaction. With a protic solvent, what's going on, and what we're going to see, is that the nucleophile ends up getting locked up by the protic solvent, and it's harder for it to get to the substrate. So the result is that we're starting from this more stable configuration, this more stable state, and it's harder to get it to the transition state because it's harder for the nucleophile to reach the substrate. When it comes to an SN1 reaction, the protic solvents are going to stabilize the carbocation intermediate, which will mean a more stable intermediate and a more stable transition state to get to that intermediate. So remember, the intermediate is represented by the trough here. The protic solvent is going to stabilize the positive intermediate. And so that's going to end up making this SN1 reaction much faster. Whereas, which is kind of the opposite of the SN2. The SN2, it ends up stabilizing the nucleophile, which makes it less reactive and thus lower in energy, and slows down the SN2 reaction. So that's what the solvent. So we got solvent here effects. So for the take-home message here is, for SN2 reactions, we're going to use polar aprotic solvents. For SN1 reactions, we're going to use polar protic solvents. And as you've seen in SN1 reactions, often the nucleophile is the solvent. That often occurs. In terms of the leaving group, so the better the leaving group, that's going to have a big impact on SN1 E1 reaction. Remember that the rate determining step in an SN1 and an E1 reaction is the loss of the leaving group from the substrate. And so if we're looking at the halogens here, the iodide stabilizes the negative charge the best. Remember, we use REO here to decide. For iodide ion, it's an atom that's big, electronegative. It stabilizes negative charges very well. And these are smaller and smaller and smaller, so they stabilize the negative less. The better the leaving group, iodide being the best leaving group, the better the SN1, and the faster the SN1. Also, the more stable the carbocation intermediate, the faster the SN1. So we've talked about now solvent, talked about leaving group. Now we're talking about the substrate. Okay, in terms of the substrate, we want the substrate to result in a tertiary carbocation intermediate, or benzylic, that's even more stable due to the resonance, or allylic, so also stabilized due to, so rather the tertiary is the most stable. Then we have these resonantly here, and so these will produce stable carbocation intermediates, and that's what's the most important to a successful SN1 and E1. Primary and secondary alkyl halides, they will just be too slow to make go through the SN1 because their carbocation intermediates will be unstable. To have a stable carbocation intermediate, you need to have a substrate that produces a tertiary carbocation, a benzylic, or an allylic. carbocation have any appreciable reaction, or it has to at least be able to undergo a carbocation rearrangement. So we'll want to be able to also decide whether the reaction will occur by a substitution or an elimination mechanism. Here. So if we look here, we have a benzylic alkyl halide, so it's possible that this could occur by SN1 or E1 mechanism. We also have a protic solvent, water, which favors SN1 and E1 mechanisms. Water not being a particularly strong base, though. And we have two possible products. We can have substitution, which we'll put an OH here where the bromine was, or we have elimination. We can't have elimination this way, right? Because this would result in a carbon with 5 bonds. So there's only one possibility for elimination. And we'd end up with a mixture of products here. So like we saw with E2 eliminations, E1 eliminations will have multiple possible types of regioselectivity, right? There's a few different constitutional isomers, or 2 specifically in this case, that are possible. Here we have, let's analyze this and make sure that this is a reaction that is likely to occur by E1 or SN1 rather than E2 or SN. So let's think about number 1, solvent. It's polar and it's protic. That's good for SN1. Right? We have a leaving group, which is chloride. Pretty good leaving group, right? We have a substrate that's a tertiary alkyl halide. Good for E1, good for SN1, right? And finally, we have a nucleophile, which is a good nucleophile. It's not a great base, but it can function. When it comes to the E1 mechanism, there's not going to be a stereoselectivity like there was in E2, because remember, this proceeds in 2 steps. We're going to have the loss of the leaving group first, and we'll have a tertiary carbocation, and then the base will come. And so then the base can come over here. Base here is water. So if we're talking about an elimination reaction, the water can come and take one of these hydrogens, or it can come these. So when it does have here proton transfer, right, and then we get a double bond here, or if we have the water over here, this proton and here. So those are the 2 possible spots for the double. Right here, and this spot is equivalent. On the left here or in the middle, we get either elimination product. Of course, the major product will be right here. Why would that be the major product? Well, it's because it's more thermodynamically stable with three carbons attached to the double. We can also have a substitution product in which the water directly attacks the positive formal charge carbon. But we can get either of those. So E1 reactions are regioselective, but they're not. But we cannot control the regioselectivity in right. So we're going to get both products. This one is a little bit more stable. We'll get a little bit of it, but we're going to get both of these products here. So also we can get a number of stereoisomers here, right? With products here. So here, when we have this elimination, we have 3 potential situations. So here again, if it's E1, we have a loss of a leaving group. We're going to end up with this carbocation intermediate. And now, when it comes to the elimination here, we have a couple of possibilities. One, we can end up taking the protons. So let's see, what are the acidic protons here for the elimination? We have one here, and then this this one or this one over here. They're the beta hydrogen. So if we remove this beta hydrogen and make a double bond here, so if this one's removed, the double bond will be right here, and that will be this product here. The double bond could also go right here, and if it does, then we have a couple of possible situations, right? We can have the one where the methyl group here is in the up position, but we can also have it where it's in the down position. So we have two here. These two are stereoisomers of one another. So the double bond's in the same spot. It's just the methyl group is either, in this case, it's cis to the other methyl group, and in this case, it's trans. So we have two stereoisomers. Or you can have a different constitutional isomers. So these guys here, compared to this guy here, these are constitutional isomers. You can have any of those products, right? In the E1 reaction will generally give the most stable alkene here. The most stable alkene is going to be the one in which you have the least steric hindrance here, and it is the most substituted. So it looks like that would probably be this one right here, even though it's considered cis. The ethyl group is larger than the methyl group, so having the ethyl group with the hydrogen on the hydrogen side is probably going to produce less steric hindrance than having the methyl group on the same side as the. So this one will probably be the major one. This one will follow up shortly after, and this one. So E1 reactions are where they're stereoselective in a sense that we're going to get certain stereoisomeric configurations, but they're not stereospecific in the same way E2 are. You won't get just one particular stereoisomer. You're going to get a mixture. When it comes to SN1 and stereoselectivity, when it comes to SN1 and stereoselectivity, again, you're going through a carbocation intermediate here. So the carbocation intermediate is a carbon with 3 bonds and no lone pairs. So it's flat and triangular. And so when the nucleophile attacks, unlike with the E2 mechanism where the nucleophile can attack from only the backside, here the nucleophile is equally likely to attack from either side. So the big difference between SN1 and SN2 reactions is in an SN1 reaction, you're going to get a so-called racemic mixture, which is a mixture that has significant quantities of both stereoisomers, R and S. So we're going to have one in which the original configuration is preserved, the nucleophile here on the right side, and we're going to have the inversion of the configuration. Whereas with the SN2, we only had the inverted one, really, right? Here we're going to have a racemic or approximately equal mixture of both stereoisomers because the SN1 does not involve the backside attack like so even though we can have a mixture of configurations obtain the SN1, typically we do get a little bit more of the inverted product than we do of the one with the same configuration. And you can see why, right? The first step is the the loss of the leaving group. And the leaving group is leaving. It does take a little time for it to get out of the way. Whereas the nucleophile can freely attack from the other side while shortly after the leaving group is left. So there's going to be a little short time blockage by the leaving group on one side while it's leaving. And so it blocks a nucleophile from attacking a little. So usually we have a little bit greater than 50% of the inverted configuration, just a little bit less than 50% of the retained configuration, because it's just slightly more difficult to attack on the same side that the leaving is leaving, but not impossible like it is in SN. So when it comes, now we've seen 4 different potential mechanisms: E2, SN2, E1, SN1. The last part of our lesson is going to be about trying to figure out which one of these reactions And we're going to evaluate that based on the based on all of the various the four various aspects that we've discussed. The substrate, meaning whether it's primary, secondary, tertiary. The reagent, the nucleophile slash base. The solvent, whether it's polar aprotic or not. Polar aprotic, polar protic. And finally, the last one is the quality of the leaving group. Leaving group. This one isn't mentioned directly here, but that's also important. But it generally seems is equally important for all the reactions leaving group. So when we come back next time, we'll talk all about how to predict which reaction mechanism, SN1, E1, or E2. Forward to seeing you then.